Thank you very much. It's great to be back at ICTS. Okay, so my talk today is titled The Black Hole Membrane at Large D. And I will be discussing a certain simplification that happens in the classical equations of gravity in the limit that the number of dimensions in which we are looking at these equations becomes large. Okay, so let me start with a one minute preview slash motivation. The idea that black hole physics has something to do with the physics of a membrane, a soap bubble type membrane, roughly speaking at the location of the event horizon, is at least 40 years old and has been expressed in many different ways. The words that often go with this feeling is the membrane paradigm of black hole physics. Okay, one way to view what I'm going to be doing today is to make, in a particular context, to make this idea precise. What I will demonstrate for you, and we'll see aspects of it, is that the classical behavior of black holes indeed reduces to the motion of a non-gravitational membrane moving in flat space. But there's a context in which the statement is true as a precise statement, and that context, at least one context, the one that we'll explore today, is the context of gravity in a very large number of dimensions. Okay, so let me just start without further ado. I'm going to study, just to say again, I'm studying a large number of dimensions. You can think of it as an approximation, to add a parameter to Einstein's equations, much the same way that a Toft added n as a large n parameter to study QCD. But our analysis is going to be purely classical. I will address no quantum questions in today's talk, perhaps for good reason. Okay, so let's look at so the equation that I'm going to be studying today is the equation Rmn is equal to 0. That's Einstein's equation in vacuum. I will sometimes extend what I'm going to be saying to the Einstein-Maxwell system in vacuum, in otherwise vacuum. Okay? So the equations I'm looking at are very simple natural equations that arise all over physics. However, what I will do is study these equations not in 3+1 dimensions as is relevant for astrophysics, or 9+1 dimensions relevant for 2B string theory, but in D dimensions, and I will be interested in the limit D going to infinity. Okay, the situation in which I'm going to be studying these equations are situations involving black holes. So to get started, what I want to do is to remind you what the Schwarzschild solution looks like in an arbitrary number of dimensions. We're in asymptotically flat space, okay? There's no cosmological constant, though it's not difficult to add that in the game later on. But we'll start with the simplest case, flat space. So the Schwarzschild black hole takes the form minus dt squared over 1 into 1 minus r naught by r to the power d minus 3 plus dr squared over 1 minus r naught by r to the power d minus 3 plus r squared d omega d minus 2 squared. Okay? So the first thing to notice about the solution, this of course is very familiar, right? You set d equals 4 and you get the usual 4-dimensional Schwarzschild black hole. Okay, the first thing to notice about this solution is that it reduces to flat space whenever r naught by r to the power d minus 3 is equal to 0, or goes to 0. Now, in a finite number of dimensions, this only happens as r goes to infinity. However, in the limit of interest to me, namely whether g is taken to infinity, this happens for every r that is held fixed greater than r naught. So if you take any r greater than r naught, hold it fixed as you take d to infinity. This quantity is 0 simply because any number less than 1 to the power infinity is 0. Okay? So the first thing that we see is that a black hole solution in flat space has a big region in the d goes to infinity region, limit, everywhere outside R0, R greater than R0, and held fixed as d goes to infinity, is just flat space in the strict d goes to infinity. Okay, that's already sort of strange and interesting. Now, the next question that we're going to ask is the following. The next question we're going to ask is, how near to the event horizon do we have to scale at large d before we start seeing that there's a black hole, before we realize the space is not just flat? In order to answer that question, we do the following coordinate change. Set r is equal to r0 into 1 plus chi by d minus 3. Then r by r0 to the power d minus 3 is equal to 1 over 1 plus chi to the power d minus 3 to the power d minus 3. And then you take the limit of large d, and that's probably the first limit you studied about in your 11th standard, at least it was the first I studied about. You get e to the power minus chi. Okay? So, what's the point here? The point is that if you hold chi fixed, r minus r0 is being scaled to be of order 1 over d. D and d minus 3 are the same because d is flat. Okay? So the point is that there is a certain thickness around this event horizon. The event horizon has size r0. There's a certain thickness about it which is of size r0 by d. There are two different distinct length scales in the problem: the size of the black hole and its thickness. This observation was made first by Emperan, Suzuki, and Tanabe about 2 or 3 years ago, where they pointed out that there are two distinct length scales in black holes at large d, and they also did a calculation to amplify one of the results, one of the consequences of this. Maybe I'll come back to that later, but I'll just move on because otherwise it's not going to time. Okay, so first thing we've learned is that black holes in large d are very simple. Outside the event horizon, flat space. Inside the event horizon, well, they're strange because this thing blows up. But for many purposes in life, we don't care what happens inside the event horizon. Suvrat cares, but many of us don't. Okay. In the neighborhood of the event horizon, things are interesting. Neither blowing up nor zero in a region of thickness 1 by d. Okay, great. Now, whenever you have two, suppose now you look at a black hole then from far away. It looks a little bit like the black hole because everything interesting that is not well suppressed by being well inside the event horizon is happening over a thickness 1 by d. And because we're interested in the limit d goes to infinity, it looks like the black hole is becoming an infinitely thin object. And so can be replaced by an infinitely thin object. Where is this propagating? Well, it's propagating in the place that you get when you scrunch this to zero, but that's just flat space. So it looks like you should be able to think of a black hole as a membrane propagating in flat space as d goes to infinity. Okay? And the point of this talk is to explain to you that this is true and explain how you can make that statement precise. Okay? Now, in order to do this, what I'm going to do is to make a construction. What I'm going to do is to find a large class of solutions of Einstein's equations that are in one-to-one correspondence with the solutions of another problem. The other problem is the problem of the dynamics of a non-gravitational membrane propagating in flat space. Okay? And the way I'm going to do this is as follows. To start with, I'll first look at what we call our ansatz metric. Okay? So you have ds square, or maybe I should write it in terms of metric. Consider the metric eta mn is equal to, gmn is equal to eta mn, that's the Minkowskian metric, plus nm minus nn minus un by psi to the power d minus 3, where nm is simply the one form d psi, so del m psi, normalized to have unit norm, where all normalizations are done with the metric eta. psi is any old function, okay? Some function that varies over length scale 1. It doesn't have d in it, but otherwise it's an arbitrary function. We're going to put more constraints on things as follows. But psi is a function, n is its normal, and is a one-form field. Okay, is an arbitrary one-form field. That's a velocity. So un eta mn is equal to -1. I'm writing this out so explicitly instead of just saying u dot u is equal to -1 to show you in what metric the norm of these things are -1. Okay, so consider this metric where psi is so far an arbitrary smooth function in flat space. And is an arbitrary smooth one-form field in flat space such that u is a velocity field. And also we will demand that un nm eta mn is equal to 0. U and eta are normal to each other in the flat space metric. Okay. Consider this spacetime. At the moment it's just a spacetime, it solves no equations, but let's look at it. Okay, what can we say about the spacetime? Well, there are many interesting things to say about it just as a spacetime. The first interesting thing to say about it is that nn, gmn, where g is the inverse metric of this, is easy to calculate. Okay, it's actually easy to find the inverse of this metric. It's just eta minus this. And that follows because the cross term, this dot itself is 0, because this is a null vector, as you can easily convince yourself with all these conditions. Okay, so it's easy to raise this metric and then just compute this. And if you do that calculation, it's a 2-minute calculation, you'll find that you get this object. Okay, so n, which was a one-form field, which was normalized to be of unit norm in flat space, deviates from unit norm in the actual metric. The point of interest of this equation is that it's 0 at psi equals 1. Okay, so what have we shown? We've shown that the submanifold of the space, which is psi is equal to 1, is a null manifold. The second thing to note about this is that if you look at the particular case, u is equal to dt and psi is equal to r by r naught. Just as a particular example, this metric here reduces to a very familiar metric. It's just the Schwarzschild metric in so-called Kerr-Shield coordinates. Okay, so particular example of this metric, particular case, psi is equal to r by r naught and u is equal to dt, just gives you the Schwarzschild metric in Kerr-Shield coordinates. Sorry, minus dt, yes, thank you. Okay, it's the Schwarzschild metric in Kerr-Shield coordinates. Okay, now in this Schwarzschild metric in Kerr-Shield coordinates, you can check that the manifold psi is equal to 1, just r is equal to r naught, is the event horizon of the black hole. So that's a null manifold, but it's not any old null manifold, it's the event horizon. You can check this. Rotating black holes, all of whose solutions are known, can also be put in this form. Okay? And you can check always that the surface psi is equal to 1. It's not any old null manifold, it's the event horizon. So, suppose we take an arbitrary metric of this form, such that psi and u are arbitrary, but at late times the metric reduces to a superposition of one or many stationary black holes, perhaps arbitrarily far away. Okay? Then the surface psi is equal to 1 in these metrics is a null manifold which agrees with the event horizon at late times, and therefore is the event horizon of the spacetime. Because that's what an event horizon is. It's the unique null manifold that agrees with the causal event horizon at late times. Okay? So for a large class of spacetimes, namely those that settle down to equilibrium at late times, psi is equal to 1 is not just null manifold, it's the event horizon of a spacetime. Okay? We will see as we go along that we will self-consistently see that this will happen. that these equations will settle the metric down into a collection of stationary black holes at late time. So in all the metrics that we will study, this manifold size equal to 1 is the event horizon. Okay, so it's a beautiful construction of a very large class of metrics whose event horizon you completely control. As most of you know, event horizons are usually very acausal things. Here in our construction, with a suitable late time behavior, we have complete control over the event horizon. Right. But psi is a real number. And yeah, okay, good. You could have -1, but we're going to look at positive psi. Psi will be a positive real number. So that's the same thing. Thank you. Okay, excellent. Other questions or comments? Excellent. So, okay. Third thing about this is for the same reason that this metric settled down, was basically flat space. If r became much larger than r0, the same phenomenon here. You see, if psi to the power d-3 is large, this metric is manifestly flat. And therefore, you can check that the precise condition is if psi -1 is much, much greater than 1 by d. Okay? This metric reduces to flat space. So this is a construction of a class of spacetimes which have a well-defined event horizon, the surface psi equals 1, and which deviate from flat space only in a thin membrane region, a thin thickness around the event horizon. Okay? So if you want a pictorial representation of the spacetimes, something like this. This represents the surface psi equals 1, and in a thin region of size 1 by d around this, something interesting is happening. Away from that, out here we are in flat space. In here, all hell is breaking loose because psi is a number less than 1 raised to infinity, but we don't care because we're inside the event horizon. Okay? It's clear that we could track the event horizon to be able to make this statement. Okay? Now, please. Where did what? Condition 3, if this happens, then metric is flat. Because if this happens, then 1 by psi to the power d-3 can be approximated as 1 plus psi -1 to the power minus d-3. Okay, divide and multiply by d-3. Okay, so you get a d-3. So this is approximately e to the power minus d-3 times psi -1. So when psi -1 times d-3 is much, much larger than 1, this can be ignored. Okay, so just estimating when that number goes to 0. Okay, great. Now, all this is great, but the key point of what I'm going to be telling you is in the following statement. It is that you might naively expect, okay, see, let's look at these metrics again. We're really interested in them in this membrane region, this region of thickness 1 by d around psi equals 1. How fast do things vary in this region? We've just estimated that. It's this e to the power minus chi behavior. This function varies over length scale 1 by d. This function varies over length scale 1 by d. So suppose I took Einstein's equations and I computed Rmn on this metric here. What should I expect to get? What power of d should I expect to get? Well, Einstein's equations are two derivatives. You can have both the derivatives acting on the fast direction, which would give you d squared. Okay, so you might expect that Rmn was equal to order of d squared. Okay, there are other ways of getting d squared actually, involving contraction of indices, which I'll suppress for the purposes of this talk. The answer is correct. Okay, this is what you might expect. Okay, I'm going to have to unsuppress that in a minute. But okay, yeah, this is what you might expect. However, the terms involving both derivatives in this r direction, in this radial direction, don't care about whether psi was how psi was changing in the transverse directions. So those terms will give you the same thing that you would get if you evaluated on a particular example of psi, namely on the Schwarzschild black hole psi. Psi is a function that is independent of d. Otherwise, no restriction. So then it cannot change on length scale 1 by d or something. Okay? It's all length scales in psi are 1. Otherwise, no restriction. Okay? So, you might think that, if you were naive, you might think that because this thing we know evaluates to 0 in the Schwarzschild solution, and because at leading order you only get contributions normal to psi, which doesn't care about how psi is changing, you might think that this guarantees that this will evaluate to, that the order d square part will evaluate to 0 for arbitrary metrics of this form. This is almost true. Do you understand the argument? You might think it's a cheap trick, but it's almost true. Okay? If you work this argument out more carefully, you have to look at other possible sources of d square dependence. And there are two other possible sources, both involving contraction of indices. You see, you could get a term which has one radial derivative and one object that's del dot u. This, although it gets its contributions, all its contributions are order 1, because it's sum over d terms, it could end up contributing at order d. Okay? And there's another source actually, which is something that is order d times del squared of psi. Let me say this more precisely, maybe I don't have the time, but very quickly. Suppose I took del square of this object. There are two terms I could get. One in which I operated the first del on this and the second del on that. Each of that pulls out a d, so I get order d squared. Another term is one in which I operate the first del on 1 over psi to the power d minus 2, that pulls out a d, and then I act the second del on the del psi outside. That looks like it's order d. However, del square again involves a contraction of indices, and so could end up giving you an extra contribution of order d. Okay? So when you work this out carefully, you find that it's not true that these metrics all automatically solve Rmn is equal to 0 at order d squared, unless the following additional constraints are satisfied. Del dot u is equal to 0, and del squared of psi. Actually, this is, okay, the condition that we will actually impose, which is equivalent, I'm sorry, yeah. The condition, see, del squared of psi is what it is in the black hole background. And the easy way of saying that is del squared of psi to the power d minus 3 is equal to 0. Because you know that in the black hole background, 1 over r to the power d minus 3 is a harmonic function. So del squared on psi is whatever you get to make 1 over psi to the power d minus 3 harmonic. Okay? So, del squared of, I wrote this here. So this was probably a bit incoherent, I apologize for that. But the end result is this. There may be something more, actually no, they can't. We've actually just evaluated the equation, the only way it works is. Yeah, if you look from outside you may have thought there was a possibility, but they appear in different equations. Yeah, yeah. Okay, so the only way you get Rmn satisfied at order d squared is if you take an arbitrary metric of this form and impose these two conditions. Okay, why was I interested in Rmn being a big 0 at order d squared? Why I'm interested in this is because I'm interested in perturbation theory. I'm trying to find a solution of Einstein's equation in a 1 over d expansion. And the key point about perturbation theory is the following. You see, in trivial examples of perturbation theory, the starting point of perturbation theory is obvious. And then you run the machinery. In non-trivial examples of perturbation theory, all of the intuition in perturbation theory goes into finding the starting point. A correct starting point is the starting point that solves the equations at 0th order in your parameter. Once you've done that, you're more or less guaranteed that if you work hard enough, you'll be able to turn the wheels. You may not be able to solve the equations, but in principle you can. And what we've done here is to find a large class of metrics that without any work satisfy Einstein's equations at order d squared. Therefore, at leading order, because d squared is the order at which you would expect them to be violated. Okay? Now, why is this interesting? This is interesting for the following reason. Suppose now I want to do better. I want to solve Einstein's equations not at order d squared, but at order d. Okay? How do I do better? Well, what I could do is to take my metric to be, let me call this whole thing G0Mn. Gmn is equal to G0Mn plus 1 by d G1Mn plus blah blah blah. I just wanted to go to the next order in d. This is all I need to do. Now, you see, we already know, and it's true, you can check by explicit calculation, that evaluating Einstein's equations at this side gives you something non-zero at order d. Evaluating G1Mn, if G1Mn is just something arbitrary, will give you something non-zero at order d square. But that's divided by 1 by d. So this will also contribute at order d. And then what the game is to try to choose G1Mn such that the two 1 by d two terms at order d cancel. Okay, if you can do that, then you found a solution to Einstein's equations that solves Einstein's equations not at order d squared, but at order d. Is this clear? So that's the game we're going to play. Now, I'll give you one, I have to hurry, I'll give you one or 2 minutes on how you do it. So you can do this. That's very simple, very simple. But I'll give you 2 minutes on how to do it and then give you the punchline. The way we did it was as follows. You see, the equation del squared 1 by psi to the power d minus 3 is equal to 0 is a great equation. You know, it's a nice equation. But anyone who's taken a course in electrostatics knows that it's not always easy to solve. You know, that's what half of Jackson is about. 1/3 of Jackson is solving this equation, right? In a particular dimension. Okay? However, so you might think that everything I've transitioned into becoming by requiring this condition, I've transitioned into becoming a mathematician, which is often a code word of doing useless things. Okay. Okay. So, you know, unless you can explicitly solve that equation, what's the point? The point is that at large d you can. Okay? Let me say this more precisely. Suppose I give you a surface. Give you a geometrical surface, and I tell you that on that geometrical surface psi is equal to 1. Then I want to find the unique solution of this equation, which has prescribed behavior of basically decaying at infinity, and psi equals 1 on this surface. Very hard problem to solve in general dimension. But order by order in 1 by d, it's very easy to generate this solution. Let me give you the solution to lowest order just to tell you what it looks like. Okay? The solution to lowest order goes as follows. Take space-time and foliate it by a set of geodesics that cut my surface. Let points in space-time be labeled by the point at which they cut my surface, x0 of m, and the distance away from this point, which is s, which is, yeah. So these are a set of coordinates in space-time. Do you understand? You've got a congruence of geodesics, each of which cut the event horizon, cut this psi equals 1 surface once. Okay? What? No doubt, I don't know. But maybe they call it Gaussian order coordinates. Okay, but it's these geodesics. Okay, and you label points by the distance away from this point and where they cut it. Then to leading order, psi is equal to 1 plus kappa by d minus 2 times s. Okay, and this kappa at x0. Kappa is kmm, the trace of the extrinsic curvature of this manifold. Okay, this might look like it's 1 by d, but the order d counting tells you that anytime you've got two contracted indices, you've got an extra factor of d. So this is actually an order 1 number, which in the case of a spherical membrane would just be the inverse radius of the sphere. Okay, so psi is equal to 1 plus distance away divided by the local inverse radius over where you're expanding. And then you can continue this expansion to higher and higher orders, to any order in S, where each of these coefficients is computed successively in a 1 by d expansion. In 1 by d, you can practically solve this equation. It's the first sign that something practically good is happening. So this parameter, same Yeah, this parametrization is not a useless one, practically useful, because you can build space-time away from psi equals 1 surface using this equation. Okay? Now, so what we do is to foliate space-time into slices of constant psi and view Einstein's equations in this foliation. If you view Einstein's equations in any foliation, there's a very natural way in which to view Einstein's equations. You break Einstein's equations, decompose into the dynamical equations and the constraint equations. The dynamical equations tell you how to evolve the metric at other psi if you know them at one psi. The constraint equations constrain data at a given psi. And it's a property of Einstein's equations that if your constraints are obeyed at one psi and the dynamical equations are obeyed everywhere, the constraints equations are also obeyed everywhere. Okay? So now we plug this into Einstein's equations. We also fix a gauge. Our choice of gauge, at the time. Okay, let me quickly tell you. Okay, our choice of gauge is as follows. This quantity that appears a lot, n minus nm, we give it a name. It's called OM. It's the null vector. Okay, and our choice of gauge is that HMN, the correction of the metric away from eta. So we write GMN is equal to eta mn plus HMN. And we choose, make a coordinate choice so that OM HMN is equal to 0, all contractions being done with the metric eta. Okay, with this choice of gauge, you can see that the most general fluctuation metric G1, and this is largely for Loga, is takes the form OM ON times some object plus OM VM plus symmetric times some object, object meaning some function. Okay, this is the V already. Okay, plus PMN times some function where P is the projector orthogonal to N and U, both. Okay, plus HMN, where HMN is a tensor function which has no trace and is orthogonal to N and U. So very much like the decomposition of metrics in the fluid gravity correspondence, for those who follow that story. Okay, V is orthogonal to N and U as well. It doesn't matter. There's some way of thinking of it in which we've got two scalar functions, one vector function and one tensor function. Okay? Now, plug that into Einstein's equations. The tensor equation gives you an equation just for the tensor. The tensor dynamical equation gives you an equation just for the tensor. Plug that in, easily solve it. Then you go to the next point. You go to the vector equation. The vector equation gives you an equation just for the vector, and that in fluid gravity it would end with being just for the vector. But here there's a new element, and that is there's a source term in the vector equation that's a divergence of the tensor solution. In fluid gravity that would have been 1 by d suppressed, but because of the extra contraction of index that 1 by d is, but because we've already solved the tensor, it's a known source term. So then we solve for the vector. And similarly, then we move on to the scalars. Okay, so we effectively decouple the tensor, vector, and scalar. All differential equations are now radial differential equations because any derivative with respect to one of these other directions sacrifices a power of 1 by d. And so it doesn't appear as your order in perturbation theory. So all differential equations are just ordinary differential equations that determine the behavior of these things as a function of the psi variable. Okay? We get a tensor equation, a vector equation, scalar equation, you can just solve. Okay? Turns out to be very easy to solve, you can solve this. No constraints so far. By the way, we solved demanding regularity, okay? Demanding regularity of our solution at the event horizon and that the solution decay at infinity. Moreover, we need the analog of the, there are two additional conditions that we impose, which are the analog of the Landau gauge condition for Loga, which is the additional conditions that we impose are that n, m, n, n, gmn is equal to 0 at all orders. So that, you could redefine your psi. Okay, I'll just write down the conditions and that gmn un is, nn is equal to u m at all orders. This you can easily check is true at the 0th order metric. But if you raise the normal with the actual metric, you get the generator of the event horizon. So UM is the vector field that points in the direction of the generator of the event horizon. This gives you complete, fixes 1/d field redefinition ambiguity of the U field and your psi function. Okay? So with these boundary conditions, regularity and so on, the dynamical equations you can just solve. What we're left with are the constraint equations. Okay? Then you can ask, are the constraint equations solved? Now, the constraint equations are solved at one side, they're solved at every side, they're solved at one side. So you can evaluate them in any place of interest. It's most convenient to evaluate them at the event horizon, at psi equals 1. And you find that the constraint equations are not automatically solved, but are solved if and only if the following equation is obeyed. This is kappa, my kappa. Where this PMN once again is a projector orthogonal to both n and u. Okay? So what have we understood? What we've understood so far is the following. That we made this construction of solutions to Einstein's equations at large D at leading order for arbitrary functions u and psi. As we've seen, the psi function is what's important is the shape of the surface, the geometrical shape of the surface psi is equal to 1. You can construct psi in terms of that. So for arbitrary shapes and arbitrary velocity fields on the shape, we've got this construction of the metric. The leading order, with basically no constraints, Einstein's equations were solved. But if you want to enhance that solution to first subleading order, you can't do it for arbitrary shape and arbitrary velocity field. It only works provided the shape and velocity field satisfy this equation. Now I want to do some counting for you. How much freedom was there in our construction of these solutions? We had to specify one shape and one velocity field. Okay. In addition to this, of course, we have the equation del dot u is equal to 0. Okay. So how many equations do we have? Here we've got d minus 2 equations. Because this vector, but orthogonal to both n and u. That removes the 2. Here we've got one equation. Total number of equations is d minus 1. How many variables do we have? Well, we've got one shape function, that's 1, and one velocity field on a d minus 1 dimensional manifold, that's d minus 2. So d minus 1. So the total number of variables and total number of equations are both d minus 1. And so this at least leaves open the possibility, and we've checked it in linearization about simple solutions, that these equations define a well-defined initial value problem for the data that goes into our construction. So now it finally feels that we're doing physics. See, because that's how physics works. Physics, our original construction had free functions of space and time. Physics never has free functions of space and time. You often have free functions of space, but the whole point of physics is to determine time evolution, to tell you the future given the present. Any free function as a function of time is suspicious. Okay? Now what we've seen is that we've got that these free functions of space and time are constrained to obey an initial value equation, and therefore not free functions of space and time, only of space. Okay. So to say it again, we've got a first order solution of Einstein's equations if and only if we've got a solution of that strange membrane equation. Okay. Now, I've got 5 minutes and 51 seconds left, so I have to hurry. Okay. This is a very intimidating thing. Okay. Okay. Okay, great. Let's move on. Now, I want to understand this equation better. Where does it come from? What is it saying? Okay. The thing that I would have to write down the solution for, and I'm not going to do this time, is, okay, there are 1 or 2 length scales I want to introduce you to. It turns out that a solution that we get, that when we do all this, we solve for this thing in order 1 by d, very much like the solution of this object here. our solution is valid over distances such that psi minus 1 is much, much less than d by kappa. This turns out to be the validity regime of our solution. D by kappa is a fancy way of saying the local radius of the event, of the black hole that makes up the event horizon at that point. Okay? So, it's telling you that the solution that you get is valid up to distances normal, small compared to the curvature of the surface. It is very sensible. However, we've already seen that this solution, even though we can find it over these regions, it already decays to something very small over a much shorter length scale. D minus 1 is, when this is much greater than 1 by d, the solution decays to a very small fluctuation around flat space. Therefore, there is an overlap regime of two different approximations. The first approximation is that of our construction, this 1 by d collective coordinate construction. The second construction is just of linearization, linearized derivative. These two regimes overlap. Is this clear? Okay? Because these two regimes overlap, we are able to take the metric that we find and continue to infinity. Because though our construction ends here, it overlaps with another approximation that continues to infinity. Okay? So, in order to understand what the solution looks like at infinity, and this is very important because we want to understand what's happening, what the radiation field is like in our solutions. In order to understand what's happening at infinity, what we want to do is to identify the linearized solution of Einstein's equations that matches with our solution in this overlap regime. Okay? Now, there is actually, it took us quite a long time to work out all the details, but there's actually something very elegant that goes on here. And that is this. It's a general property of linearized solutions of Einstein's equations in the large D limit. And that goes as follows. Suppose I give you the linearized part of Einstein's equations in some region here. See, there's a small subtlety that let me mention. You see, it turns out that if you look at the reasonable solutions to these linearized equations, there's a solution that decays very fast, like 1 over psi to the power d minus, and another solution that grows very fast. Sort of like psi to, okay, like 1, or in natural units like psi to the power d. So that grows, doesn't matter how fast. Okay? The reasonable solutions of the linearized equation have linear combination of both the growing and the decaying piece. But the coefficient behind the growing piece is extremely small. In fact, of order 1 over d to the power d. For this reason, until you go very far away, you don't see the growing piece at all. Because though it's growing, it's suppressed by a very large coefficient. In fact, you only start seeing this growing piece at psi minus 1 of order d. Okay? Turns out, okay, I could explain it more. There are questions. Okay, now, our construction of these solutions is in the 1 by d expansion. And so we are blind to things like 1 over d to the power d. So all we see is the decaying part of the solution. What we really capture is the decaying part of the solution in this region. You can see that explicitly in our solutions. However, there is a very elegant thing. Suppose I'm given just the decaying part of the solution to Einstein's equations in the region outside a membrane. Linearized Einstein's equations to the region outside a membrane. And I want to characterize this solution. It turns out that there's a one-to-one map that you can effectively construct between the solution and a source on the membrane. A stress tensor. Okay? And that stress tensor is given as follows. You take the solution, draw it back to the membrane, and compute the Brown-York stress tensor. Extrinsic curvature minus k GMN. And then subtract the contribution of a local counter term on this surface. And the local counter term is completely determined by the requirement that the stress tensor vanish in flat space. And turns out to be given up to some number which is not very important, important in detail, but I'm not going to tell you about. Square root g by square root r. This is a local counter term. Oh, and this local counter term exists in every dimension, but we can only construct it in 1 by d approximation. So the next term, for instance, is del squared r by r to the power 3 by 2. What? No, it's only got a finite number of derivatives. R is a local quantity. Ricci scalar of the induced metric on the membrane. Okay? So if you just know the metric at that point, you can construct it. Exactly. So what you have to do is so in the entire effect of this nonlinear part of gravity, as far as stress tensor is concerned, is summarized by an effective action. And this you can derive. This effective action is just this object. No. This, you cannot, the Brown-York stress tensor is just K Mn minus K times Gm.
But there were people who then added some funny counter terms like this too.
I don't know what they've added, but I've never seen this before. You do?
No, that's an ADS. In flat space.
In flat space, if you go to infinity, it presumably simplifies to something smaller, because then you can expand that R. That's probably what they added. But this is just true at finite distance. Okay? So now what you can do is, I emphasize that this thing is a general map that is true in every dimension, but it's extremely non-local. Hard to construct explicitly in finite dimension. But in infinity, you can systematically in 1/d expansion construct it. Okay? So now, there's a nice map between these solutions and a stress tensor. And that map has the property that if you take that stress tensor and convolute it against a Green's function, it will bring back your solution. Now, what I said sounds ambiguous, because Green's functions are not unique. You could have decaying, retarded Green's functions, Feynman Green's functions, advanced Green's functions. But there's another wonderful property of a large D that comes to your rescue here. And that property is that all Green's functions agree with each other up to terms of order 1/d to the power d at distances of order 1. This is in fact the same statement that the growing part of the solution always comes suppressed by 1/d to the power d. The Green's functions have a universal decaying part and differ in their growing part by a very small amount until you go very far away. Okay? So up to 1/d to the power d corrections, there is a map that tells you that no matter what Green's function you use, convolute against this stress tensor, you'll reproduce your solution. Now, in our physical problem, let's say you've got some black hole doing something. You know that nothing's coming in from infinity. So we know what Green's functions we want to use. We want to use the retarded Green's function, because we've got a boundary condition that at infinity, all radiation is only outgoing and not ingoing. This is the nonlinear version of the boundary conditions you put for quasi-normals. Okay? So this is a general map for the stress tensor. This is how you construct the stress tensor from our solution. And once you constructed the stress tensor, you can compute radiation by convoluting it against a retarded Green's function. Okay? Let me give you the formula for our stress tensor. I'm over time, but very briefly. Turns out that Tmn is equal to kappa by 2 un minus kmn. I'm telling you about first order, okay? Del m un plus del n um. Okay, minus half del n kappa by kappa plus symmetric. Okay, what do I want you to take away from this stress tensor? This first term, which is actually the dominant term at leading order in large D, is the stress tensor of dust. Okay, moving along the generators of the event horizon, the density of the dust being given by the trace of the extrinsic curvature. This term here is a shear term. Okay. The coefficient behind this is what you would call shear viscosity. And if you compute the ratio of the shear eta by s, you find, surprise, surprise, 1/4 pi. Okay? This term here can be absorbed into a redefinition of the velocity. It's just there's some shifted velocity that pulls it into this because it's 1/d suppressed compared to this. This term is genuinely new. It's a tensor perturbation proportional to Tmn that comes about because you're not working in flat space, but you're working in this funny twiddling thing. So this is basically like the stress tensor of dust type fluid with a shear term and a new term which indicates forcing due to being on a strain surface. It's a very simple stress tensor. Okay? Okay, great. Everything that I've said here can be redone at second order, next order in the 1/d expansion. We had a paper that I think was in the archive today that gives the details of that. You expand, the equation of motion is corrected, the stress tensor gets corrected, but the structure remains the same. In fact, in our paper today, we argued that this perturbative procedure can be carried through with no obstruction to every order in the 1/d expansion. Okay, almost done, almost done. Okay. There's one new qualitative feature, though, that comes about at second order. And that qualitative feature is that this equation gets deformed. This equation, which was del dot u is equal to 0, in fact turns into the equation del dot u is equal to 1 by kappa times a number which I'm not writing, times sigma mn, where sigma is the shear tensor. It's this misses. Okay? Now, I don't have the time to describe any of this to you in detail, but it's possible to write down an entropy current on our membrane. Okay? This entropy current, when integrated, produces the area and has the property that its divergence is always positive definite. Okay? And it turns out that to 0th and first order, that entropy current is very simple. It's just simply um with no other coefficients. And therefore, this equation del dot u is equal to whatever gives you the divergence of the entropy current and is a term proportional to sigma square. So it tells you that the only configurations of this membrane that are not producing entropy are those with zero shear. And the only such configurations are rigid rotations. So you have this nice proof of the no-hair theorem of black hole physics. Okay? That translates into you can classify all rigidly solution. Last 1-2 sentences. We've redone all this with charge as well. Okay, Einstein-Maxwell equations. You get a charged membrane, a new equation that in addition to this, which tells you how charge diffuses. That equation. Oh, what did I forget to tell you? The important point I forgot to tell you is that this stress tensor, because it couples to radiation, has to be conserved, because otherwise the coupling to radiation is not gaugeable. And the conservation of the stress tensor, you can check, is simply a rewriting of this equation of motion. This equation of motion is simply the statement of conservation of the stress tensor. Okay? Similarly, for charge, we've got a new equation of motion, a new charge current on the membrane, and the conservation of that charge current is simply a statement of the new equation of motion. Okay, so that's it, unless there are questions or comments about anything. To summarize, what do we have? We've established in large D a one-to-one map between two different dynamical problems. On the left-hand side, we've got solutions of Einstein's equations that have particular properties. I haven't even had the time to tell you what these properties of these solutions. You can ask me questions. On the right-hand side, we've got solutions of a non-gravitational problem, the hydrodynamics of a membrane whose shape is also fluctuating. Okay? This, in my mind, realizes this in a precise particular concept, this idea that has been floating around but was never usefully precise in my opinion, the idea that black hole physics has something to do with the membrane. Okay? The context in which one context in which it makes sense is large D. What this is useful for, I don't know, I could speculate if there are questions. Okay. I suppose one could, yeah, maybe it would be rather trivial for scale. We probably, you see, unless there was some reason to force the scalars to be turned on, the scalars would just be 0. Because that's a consistent truncation of the equations. Now in ADS, there was a similar question. Right? You could take the Einstein-Dilaton system. And in ADS, there was a natural way of forcing the scalars to be non-zero by just perturbing the scalar at the boundary, turning on the source for them. Here we could do something similar. Okay, there's lots I haven't had the time to tell you about. But here we could do something similar. That is, we could look at black holes not in vacuum, but black holes in the presence of a gravity wave. You know, so far what I've told you is what happens to a black hole as it's, you know, let's say you take two black holes, they bang, then this black hole sort of vibrates, settles down. I'm describing that motion. The space-time other than the black hole was just flat. But you could ask other questions. What happens to forced black holes? A black hole that's sitting there is forced by a gravity wave coming on it. Our construction is easy to generalize to those cases. Okay? Then the scalar thing would be interesting. Yeah, we could generalize to scalars. Please. Okay, yeah, I have a clear thought about that. It does not exist except in the sense of Loganayagam. Okay? Because these equations of motion, as I've only briefly had time to allude to, are highly dissipative. Okay? You can see that from the fact that entropy is being produced. Okay? But a more clear, a more straightforward demonstration of that is this. You can take these equations, one of the simplest solution is a spherical membrane. Now you can take these equations and linearize them around the spherical membrane and check what the spectrum of linear solutions looks like. And the spectrum of linear solutions are all decaying, in fact decaying very fast, okay? Except those solutions that correspond to changing zero modes of the black hole, okay? So since we've got dissipation, we don't have Lagrangians unless you do something more fancy, okay? So this you should think of in the framework of hydrodynamics. These are basically equations of hydrodynamics on the membrane. And hydrodynamics, to first order you shouldn't ask questions about actions in hydrodynamics. To second order, you're Loganayagam. Okay. Okay. Okay, I have done nothing in flat space. However, the basic idea here, okay, now if you're an ADS, it depends on what the length scale of the ADS is. Suppose we work with ADSs whose length scale is 1 in the large D limit, then the basic thing is very little changed. Shayantani and collaborators are in the process of generalizing this stuff to ADS and de Sitter backgrounds. And to first order, if I hope I'm not reporting, yeah, okay, but anyway, they tell me that to first order they find no change in the equation of motion, except that these equations, which were equations on the world volume of the membrane, now become covariant equations on the world volume of the membrane as regarded as submanifold in ADS. To second order, yeah, you can do all that. Yeah. So there's a rich story that you can, there's a lot of physics you can investigate with this. Actually, you can do it for any reasonable Einstein equation coupled to any reasonable matter as long as there's no D appearing in the right answer. So if you're interested in any sort of physics at large D, there's very rich structure to explore. Let me say one more thing about that since you brought it up. Am I allowed? Okay, okay. You know, this business about what this stuff might be useful for, which is where you were going. I have one suggestion, which I don't know if it will pan out, but I don't know, I find interesting. And that goes this way. One of the things that we managed to understand within Einstein gravity is the second law of thermodynamics for these membranes. Now, over the last 5 or 6 years, there's been an explosion of understanding on the constraints of the equations of hydrodynamics that result from having a second law of thermodynamics. Okay? Most completely in Loganayagam's, Logan Mukund's recent work. You completely understand what the constraints of the second law of thermodynamics are on the equations of hydrodynamics. These guys here are equations of hydrodynamics with one new twist. It's in gravity we understand the second law. I don't think it would be difficult to extend the classification of Shayantani and Loganayagam and Mukund to understand all membrane equations, the constraints on membrane equations that are consistent with the second law. That sounds possible. Now, why is that interesting? I think that's interesting because it's dual to a very interesting problem, interesting open unsolved problem. The constraints, you see, the open unsolved problem is this. Higher derivative gravity is known to have an entropy function in equilibrium that obeys the first law. But nobody's ever understood in completeness, bits of understanding, what the constraints on the equation on the alpha prime expansion in high derivative gravity are, if any, that result from the existence of a second law. Or, more practically speaking, what the formula is for the time-dependent entropy function that always increases in time in high derivative gravity. This is a question that many of us have thought about various points in many people have thought about. I believe that this might be a tool to help answering that question. Because you see, our membrane, unlike the fluid gravity membrane, lies on the event horizon. It's insensitive to what happens far away. So in some sense, the hydrodynamics is the hydrodynamics of the horizon. And so what we've done, I think, is to translate that question of increasing world entropy into a question of hydrodynamics, which I think should be easily solved. So this is the kind of thing, apart from getting approximation schemes to finite D for questions you might be interested in, if there are interesting issues of principle, there are issues that are rounded every D, I think you might be able to address them effectively at large D. This is often how, the way in which extreme limits are useful, not so much as approximation schemes, okay, that's for experimentalists, but for issues of principle. If you have any other suggestions for problems that require an in-principle answer that we could address at large D, I'd be very interested. Why? Oh, for alpha prime expansion. However, the question of walled entropy is just a question in classical gravity. Walled was not specialized to D equals 10. So the question you can ask in all dimensions. Yes. This may not, but I'll give you the fantasy, which is often how ADS-CFT works. You understand in the special case how it works, and then I understand you can generalize purely gravitationally. But at the moment, in my opinion, we have no understanding of this. Yes. So the many things that I've not told you about. One of the things is this. You can classify all stationary solutions of these membrane equations. Okay? As I told you, the stationary solutions have to be rigidly rotating. When they're rigidly rotating, the shape of these solutions puffs out because of the centrifugal force. You can just find these solutions. And these solutions, you can check in great detail, are the duals to curved black holes. So let me emphasize. What we are doing is to find all dynamical solutions involving black holes that have timescales of order 1 rather than 1 by d. Simple examples are stationary solutions like curved black holes. But much more important is we completely control dynamics. So if you want to understand black hole collisions in large D, it translates into the question of collision between two soap bubbles governed by these equations. Very interesting dynamical things can be understood.
So thank you.